to corral today. That's good. It means you like talking to each other. Welcome to our Wednesday seminar. Today we will hear from Jeff Heer, who is an associate professor of computer science at the University of Washington, where he works on human-computer interaction, visualization, and social computing. The visualization tools he developed by his lab, D3, ProViz, Flare, Prefuse, are used by researchers, companies, thousands of data enthusiasts around the world, as well as people right here at IHME, including some of you who took my class this summer. That was a blast. And his group's papers have received awards at the premier venues in human-computer interaction and information visualization. And Jeff is a professor at the University of Washington, I said already at the beginning of this, and has been for the last 2 quarters. So I think this is his first time joining us at IHME. So let's make him welcome and hear a great talk.
Great. Thanks a lot for the introduction. It's a pleasure to be here. As he said, my name is Jeff Hare, and I am someone who studies human-computer interaction and data visualization. And many of the projects I'll be talking about today were actually done kind of in the previous 5 years when I was an assistant professor of computer science at Stanford University. But I am happy to say, as he pointed out, I've traded in my cardinal for a more royal hue. And so I arrived here in the late summer, and it's been a great time being here in Seattle, and very nice to meet all of you as well. And so the title of my talk is Interactive Data Analysis. So obviously data is a big topic this day. It's almost sort of deafening the amount of conversation going on around topics of big data involving many exciting issues such as large scalable systems, machine learning, et cetera. Those are all very important, but I want to focus on today is more sort of like the last mile of data, which is basically the people component. How do we think about data? How do we reason more effectively? What are the tools and representations that allow us to use data technologies in a way that informs our decisions and lets us act with more confidence and reliability in the world? And so to do that, we draw on lots of different inspirations. So certainly work in visualization is one focus, statistics, machine learning, data mining, all of these things really come together in the things we care about. And so I can think of no better protagonist to really kind of start this talk with than the statistician John W. Tukey, who many of you are probably familiar with, and certainly one of the most preeminent statisticians of the last half century, famous for popularizing or designing many different techniques. And what I really found exciting was a writing he did back in 1965. It's a paper he did with Martin Wilk called Data Analysis and Statistics, where he tries to chart what are the trends in the way that we're working with data and what's needed in response. So I'd like to share with you some quotes from this article, again, almost 50 years old. He wrote, 4 major influences act on data analysis today. 1, the formal theories of statistics. 2, accelerating developments in computers and display devices. 3, the challenge in many fields of more and larger bodies of data. And 4, the emphasis on quantification in a wider variety of disciplines. So, as you can tell, the 1960s were a very, very different time than now. Right? So what does he go on to say given this? Well, some of the influences of statistical theory on data analysis have been helpful. Others have not. Exposure, the effective laying open of the data to display the unanticipated, is to us a major portion of data analysis. Formal statistics have given almost no guidance to exposure. Indeed, it is not clear how the informality and flexibility appropriate to the exploratory character of exposure can be fitted into any of the structures of formal statistics so far proposed. And he goes on, nothing, not the careful logic of mathematics, not statistical models and theories, not the awesome arithmetic power of modern computers, nothing can substitute here for the flexibility of the informed human mind. Accordingly, both approaches and techniques need to be structured so as to facilitate human involvement and intervention. So really, at the center of data analysis, despite all the different techniques and methods and technologies we can develop, is the informed analyst, the person with the question and their ability to interact with the data at multiple stages of analysis. So let's just look at one example that puts this into practice in a modern context. So this is actually a visualization of data taken from Facebook. And in fact, this is actually a couple years old, but this is my personal network from Facebook. So this is all of my friends and the connections between them. So what do you see here? Well, circles are people. The gray edges between them represent friendship relationships. In addition, in this case, we size the circles by a statistic called betweenness centrality. So basically, how central is someone in the network? If you're going to take random walks from one person to another, basically how far are they in the middle of the network, something we show here. We then use a technique called force-directed layout, where edges act like charged particles that repel each other. Edges act as springs, pulling them together. Then we find a low-energy configuration of that system to give us, hopefully, a nice interpretable layout. So that's one way we use visualization to try and understand a potentially complicated data set. And so what do we see in this case? Well, quite frankly, we see 3 blobs, right, roughly. So there's one very large cluster in the center, and then 2 satellites. Turns out this here in the center corresponds to folks that I knew in graduate school, people in my research community, people kind of connected through academia in that way. And then I have other friendship circles from undergrad and high school that you can see as satellites. Well, what else can we tell? Well, it's really hard to see the connectivity of the patterns here because it's so dense. So what's going on in the center of this cluster, this big community, it's very difficult to see. Some of you familiar with social network analysis may be able to pick out some other patterns. So for example, the central blob has what we call core periphery structure. You have a dense core surrounded by a more loosely connected periphery. So we do get some insights into the data, but there's probably many more questions we'd like to ask. So what could we do? Well, one thought is to change the representation. So here we use what's called a node link diagram. It's one sort of intuitive way of showing a graph. But as we might guess, it doesn't scale well as edge density goes up, the amount of connectivity. So here's an alternative representation. So this is an adjacency matrix. So what we've done is really put the edges forward. People are now represented as rows and columns of a table, and then we fill in a cell, we color it if there's an edge between them. In addition, what we've done is sort the rows and columns, basically a statistical technique called seriation, where we permute the rows and columns such that people who are highly connected to each other are more likely to be placed together. And the idea behind doing that is to show clustering structure within the network. And so we actually see those same 3 blobs as before, but in a slightly different configuration. One of those blobs is down here. Another one is actually right here. But then these other 3 groups, up in the upper left, here and here, are actually substructures that we can discover within that initial big cluster. So what we couldn't see but now begin to see here is that there's actually 3 subcommunities within that large community. Turns out one is the human-computer interaction research community that I'm part of. One is the computer science department at Berkeley, where I did my PhD studies. And the other is the School of Information at Berkeley, where I took half of my coursework while I was there. And so you actually see that there's this interesting substructure that we missed using the first visualization. So part of the issue here is how do we have the informed analyst in the loop with an easy access to these different types of representations so they can quickly ask these types of questions. And at this point, we might start feeling more confident that we understand the structure of this data. Then we might start applying analytic algorithms. So for example, if I were Facebook or Twitter, I might be interested in link prediction to suggest friends to you. But I would suggest that we maybe be a little premature in taking that step. So one of the things that you always want to do when analyzing data is not just hunt down interesting patterns or look for that hypothesis that you're excited about. It's also to exercise skepticism. What are all the assumptions that you make that you should check that the data may or may not support? So for example, let's take this same representation, but just order the people, the rows and columns, in a different way. So here I've resorted the data, but now it's by Facebook ID, which this actually turns out is the order in which this data was returned to me by the Facebook API. And if you're familiar with Facebook ID, what it is just a counter that basically when you join the service, you get a higher and higher Facebook ID the later you join. So what do we see that jumps out in this particular view? Right, there's a giant white square. So what does that mean if we interpret this literally? Any thoughts? So right, this is sorted by Facebook ID, which is basically a counter when people joined. So if we interpret this as is, what it's saying is that newcomers to Facebook don't friend each other. And we have lots of reasons to think that that's probably a very dubious thing, for a number of reasons, not least of which is you never see patterns this perfectly clean, right, in any real-world data. So what's going on here? Well, this actually, I didn't know. I saw this. I'm like, there's something fishy with this data. So I dug deeper, and it turns out what happens is I wrote a single query to Facebook to get all the data. And it turns out they silently enforced, at least at the time, a 5,000 result limit. So basically, I was only getting a small fraction of the data, whereas if I had done something stupider in a sense and just written one query per friend, I would have actually gotten the entirety of the data. And the important point here is if I wanted to make conclusions about this data, if I wanted to do modeling, I would be putting garbage in the sense that I'm missing perhaps up to 20% of the data that I care about. Something that was completely missing to me in these views here, and also something to which most analysis algorithms would be completely blind. So the important part here is thinking about what are the representations and tools that let us explore and interrogate data, but also allow us to express our skepticism and our domain expertise. And so, of course, visualization, as I've shown here, is one piece of the puzzle. And while that's a focus of our research at my group at UW, it's important to point out visualization is just one piece in a much larger process. That's the life cycle of data analysis that involves how do we acquire data, where does it come from, how do we clean and prepare data, how do we join disparate data sets together that might have never been intended to be brought together, how do we visualize it, model it, how do we share our results with the world at large. And while it might be convenient to think of the process like this, and many tools make this assumption, I'm sure many of you in the room who've worked with data have experienced something much more akin to this. Where you get new data, you start going forward, you might be building models, visualizations, you realize some fundamental flaw, whether it's a wrong assumption or missing data, and you go through these iterative and interactive loops of trying to make sense of the data and get the highest quality insights and results at the end of this process. And so really the research goals that my group has is to study this process in its entirety, identify the critical bottlenecks, and then figure out how can we develop new research tools that help people conduct analysis more effectively. Or alternatively, in conjunction with that, make analysis more accessible to much broader audiences. So in the remainder of my talk, I'm going to kind of use this as a rubric for walking through some of the projects that attempt to do this. So let's start kind of earlier in the process with the problem of preparing data for analysis. So as you may know, data arrives in many, many different formats. And in fact, to understand these issues better, we did an interview survey where we went out to 25 different companies, talked to 35 different professional data scientists, tried to get a sense of what they went through in their day. And here's a representative quote from those interviews, which is, "I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all." And when we talk to others, the first reaction we get with this quote is either, "Oh, yes," or 50% is much too low an estimate. In fact, DJ Patil and others who study this have written books write something more like 80% on average. And DJ ran the data science team at LinkedIn, where he says 80% of the productive working time of his team was on prepping data prior to actually building analytic products. So I think of this problem as something of the elephant in the room of data science work. It's like something that we're all doing, but until recently really weren't talking about. And so this kind of opens up really interesting research questions. Certainly, the database and statistics communities have been interested in problems of dirty data, missing data, et cetera, for decades, and have a number of really fantastic techniques that we can apply. But the core problem is that it's a problem that we can't just automate away. It requires domain expertise and interpretation of the data to know which techniques and assumptions are appropriate. And so I think that also, to me, suggested that at the core of this issue is also a human-computer interaction problem. Can we build better user interfaces to put people at the center of accelerating data preparation tasks? And so this led us to a number of projects. Here's one representative data set, just to show this isn't an academic exercise. This is your taxpayer dollars at work. So this is actually housing crime data, of course, years in different states, that's freely available from the Bureau of Justice Statistics Department. But go ahead and I challenge you, go load this into R or a database or a visualization tool like Tableau and see what happens. Well, formatted well for humans to read, this is not something that's a usable format for computational tools. So how do we easily transform this data? Well, currently you either spend many tedious hours in tools like Excel, or you write out one-off scripts in languages like Python or Perl to transform the data. So can we turn this into an interactive process? That was the question that we looked at in a project called Data Wrangler, which was primarily driven by my former PhD student, Sean Candle. So let me just jump right into a demo to show you how the system works. Apparently I'm supposed to give a talk to you. Okay, let's put that away. Here we go. Okay, so we'll start with data. This is a simplified version of that same housing crime data set I showed you earlier, just simplified to make the demo tidy. So we'll go ahead and click Wrangle, and we bring the data into this tool. And so the first thing you probably notice is we have kind of a familiar spreadsheet-like UI, basically a data table where the data has been brought in. And in the bottom left, you can see a history of operations, and we can see a couple things have been done already. So we split the data, based on new lines into rows, and then we split it into columns based on commas. So we recognized a comma-separated value format and just applied that. We could, of course, undo that if that was an error, but in this case, it's the right thing to do. So now what can we do? Well, there's a number of commands along the top, and you could imagine issuing different transformations. But really what we want to do is allow you to directly interact with the data. So for example, one thing I might be concerned about is these empty rows. I don't need them. So I can go ahead and just click that row. And in doing so, the system searches over possible operations that I could do. So in this case, just delete row 2. And that's not what I want, but the system also saw that the row was empty, so it generalized along that dimension. And the second suggestion, selected when I hit the down arrow, deletes all empty rows, and then uses a visual preview, so we see visualize the effect of the transform here to be able to assess if it's doing the right thing. So this looks good. I can delete all empty rows, so I go ahead and hit enter. The data table updates, and so does my script of operations in the bottom left. Now, a bit more complicated is I need to pull out these state names, right? Because I have this data for years and a crime statistic, but the states are in separate rows. So how can I pull those out? Well, I can go ahead and just start selecting text. I'm interested in Alabama, and it correctly guesses I want to do an extraction, but it starts with some very simple extraction rules, like basically the indices in the string, basically what position in the text are those characters, or matching the word Alabama exactly, which would be great if I wanted to count how many times people talk about Alabama, but in this case, that's not what I want to do. And I can see that it breaks. Alaska's too short, Arkansas is too long, et cetera, for the current rule. But I can just go ahead and start giving it more examples. Here, selecting Alaska. And in doing so, I'm basically pruning, decreasing the size of the space that the program is going to search over. And doing now, I now have a nice extraction rule. This looks good in the visualization. And then if I read the text on the left, it basically is pulling the word after the text in, which turns out to be very good for this data set. And I could, of course, scroll down further if I wanted to check for subsequent rows if this rule would still work. So that looks good. So I'll go ahead and hit enter. And now I've extracted the state names out into their own column. And as I'm doing this, you may have noticed some other features of the UI. So for example, there's a little number icon in this column. So we're actually looking at the data and trying to infer the underlying data types. And then so what you're seeing above the column here in green is all the values in that column that parse correctly as numbers. And then in red, all those rows that don't. And I can click it to select those. Similarly, over here in gray is shown all the empty cells, so all the missing values. And so I could click this to get suggestions as well. Here, the first suggestion is to delete those rows, which is probably not the right thing to show as the first suggestion. But we can go ahead and look at some of the others, including interpolation. And because it's string data, interpolation here really just means copying or filling in. So we can fill down, and this actually fills out the column in the way we'd like. So I go ahead and hit enter, and now I've added this to my transformation script as well. And now I really just have these rows I no longer need. And so I could, of course, throw away things that don't parse here. I could throw away things that are empty there. But those transformations could be brittle. I mean, maybe there's a typo for a year that I'd like to correct as opposed to throw away. So to be safe, I'll just go ahead and select the text reported crime in, because I want to delete the rows that have that text in it. So doing so, it first guesses that I'm trying to do an extraction. But then here I can give it a hint and tell it, no, I really want you to look at deletion operations. And you see now it's inferred a deletion that has the predicate that I want, that is, where the first column starts with the text reported crime in. So this is great. Now I have a good query for deleting this data, and I can go ahead and do that. And now I do have a clean data set. I have greens all the way across the top, which is a good sign. And so now I have something I could actually load into a database. But OK, that's great. I could rename my columns, of course, and I could then hit export. And if my data set's small, I could export it as column separated values, as JSON, JavaScript object notation, et cetera. And that's great. But what if I have a really big data set? This is a browser-based application, so there's obviously severe limits on the amount of data I can bring directly into the tool. So what can we do then? Well, actually what we can do is actually just sample the first 100 or first 1,000 whatever rows of the data set, bring this into the tool, work with them, and what we've done is not just transform the data, but here in the bottom left we've actually built out a program with all of the operations that we're going to apply. And while this looks like pseudo-natural text in the bottom left, this is actually rendered out statements that were actually stored in the computer as statements in a high-level programming language of our own design. So we can take this transformation script and then compile it to the platform of our choice. So here we can generate Python code that implements all these transformations. So I can take the code and then run this at scale back on my computer. So I can maybe pull in 1,000 rows and then get back a program that I can run over millions or more rows of my data set. And we've done this for things like SQL queries, JavaScript. Within the lab, we also built things that produce MapReduce programs. So we can actually run this at scale across a cluster. So the goal here, again, is to be able to interact with data, transform it, but then on the result also have an output that's scalable. So really what we're doing is creating programs by directly interacting with our data. So that's the idea behind Data Wrangler. And so if you want to play with this more, it is online. So there's an online example. It's not perfect. It is a research prototype, but it's freely available here. So go ahead and certainly send us feedback. We always like to make it better. We've since taken these ideas and actually brought them into the marketplace. So Sean Kandel, as well as our colleague Joe Hellerstein at Berkeley and I, started a company called Trifacta, which is actually providing a version of this software that's sort of souped up and runs at scales across big data clusters. So if you have data transformation needs, go ahead and take a look at Wrangler. And if you have bigger scalability challenges, come talk to us at Trifacta. Yeah, question?
So when it makes suggestions about what to do with the data or column, was that heuristically determined? Or
right. So great questions. Basically, what did you do to do the transforms? And I didn't include those slides directly in the talk, but just to give you a quick sense. First of all, we've designed our own programming language. And the nice thing about doing this is it's a domain-specific language, or a DSL, that's really tailored at the problems of data transformation. So by doing that, we actually have a formal structure over which we can search for possible statements. And by design, we've kept that structure rather compact. So you might imagine for a fully featured programming language, the number of statements you'd have to search over would be way too large. So we've already sort of reduced the problem there. And then we have a combination of both heuristics, like for certain keys, but really what we do to do ranking of the possible transforms is we actually have a corpus of prior transformations across a large number of different data sets. So we can actually look at the statistics of basically the frequency of transformations people have done in the past. So basically do a really easy, cheap form of maximum likelihood estimation to then rank the different transforms that our search routine generates. Of course, we prune it by the things that match the user inputs and all of that stuff too. If you want more details, come talk to me after the talk. So that's one issue in data cleaning. And so once your data is prepared, really now you're just getting started, right? So what can we do next? Well, let's talk a bit about some issues in data visualization. So once the data is nicely structured, then we're really at a place to start creating graphical representations of that data. So one question naturally is, how might we support expressive and effective visualization designs? So how can we make visualization designs that work for people to understand data, but are also not artificially constraining the space of the types of things that we can build? And so we actually have a long history of doing this in our lab. And so I just want to share with you one project that many of you are already familiar with, which is D3.js. So we've actually built a number of systems over the years, and this is currently our flagship product, if you will. This is an open source library for building web-based data visualizations. So before we talk about this in more detail, let's just jump in and see some of the things that we might want to be able to build. So one of the great things about working in visualization is that it has this really rich history. So visualization certainly spans millennia, but it's really only in the last couple hundred years that the modern forms of statistical graphics have really taken shape. And so one of the sort of progenitors of modern data visualization is William Playfair, who is a Scottish iconoclast and among other things can lay claim to being the inventor of the pie chart. So it actually has a very recent 200 or so year history. And this is a visualization that he originally designed by hand. So this is really one of the first economic dashboards, really, is the rise of capitalist and mercantilist economies. How is England doing within its own interior economy? Where here we see the wages of a mechanic, and it's plotted against the price of wheat here. So basically, are price controls working in such a way that the employees, workers can still afford to feed themselves? And if the answer is yes or no, and you want to know who to praise or blame, the reigning monarch is listed across the top of the chart here. So this is an example, sort of a classic hand-drawn visualization that, of course, we've been able to rebuild using our tools. And so we thought looking at some of these classics that were originally drafted is a good sort of challenge case for computational tools, as opposed to simple things like recreating Excel charts, et cetera. Here's another classic graphic. This is a Coxcomb of Crimean War Deaths by Florence Nightingale. So this is actually a public health policy visualization. Rather exotic way of showing a time series. Each wedge is a month. And then encoded in area are these overlapping sectors. So what you see in red here is the number of deaths due to battlefield injury. Black is other, and blue is deaths due to preventable disease. And so obviously a weird representation that Florence Nightingale chose on purpose, really to show that the biggest enemy of the English army in the Crimean War was bad hygiene. And she said, well, why not use a table or a simpler representation? And she responded, well, I wanted to affect through the eyes what we failed to convey to the public through their word-proof ears. So this is actually an example of using visualization as a rhetorical device. So in this case, using something that may not be as perceptually effective at seeing the actual data values, but was meant to grab the attention of viewers to make them aware of a pressing public policy issue. And of course, no visualization tool will be complete without the ability to recreate what Edward Tufte called possibly the greatest statistical graphic ever made. I'll let you be the judge of that. Charles Minard's depiction of Napoleon's march on Moscow. So here you see what we call a flow map, where you see the French army marching east into Moscow, returning decimated to sub-zero temperatures along the way. So these are some classic visualizations, and we of course want to be able to recreate those. We also want to be able to support interactivity as well. So here's a very simple visualization, a time series chart, encoded as area. But we want to be able to see it at multiple granularities. So we have an overview down here, and by dragging out a region, we can then examine further focus regions in more detail. Well, that's for one dimension of data. Moving up to higher dimensions, there are a number of techniques. Here's one called the scatter plot matrix, or SPLOM, which in this case showing plant data collected and very popular with statisticians. This is actually used by Fisher to develop the technique of linear discriminant analysis. But what we're seeing here is really just all pairwise scatter plots for quantitative data. So it's a way to try and get insight into both correlations among dimensions and hopefully a glimpse of higher dimensional structure. And we can, of course, marry this with interaction techniques such as brushing and linking, which is here I brush out a region and then I see linked selections across all the plots. So having identified a cluster in one view, I can then get a sense of how that cluster may or may not be preserved across other projections of the data set. Then, of course, I can drag around to then interactively explore the data and look for different patterns of projection across the various dimensions. This is a way of basically showing all pairwise relationships at once. There are, of course, other multivariate techniques as well. This is a one called parallel coordinates, which is a bit perhaps somewhat intimidating, but with some use actually becomes quite helpful. And what we're visualizing here is 7 dimensions at once. So basically imagine a spreadsheet with 7 columns, and then we're showing all of the rows. And what we do is that for each column, we then form an independent axis. And of course, you could plot all the data for that column along that axis. And then for any row in the table, we then just connect all the points with lines. So each line that kind of moves through here is basically one record of your database. And we can start to see some clusters and groupings when lines cross that suggests inverse correlations, for example. So we can start to see some interesting patterns. We see even more when we start to drag out regions, use a technique of dynamic queries to be able to explore the data. So for example, here I can select only all the cars that are really heavy. And perhaps unsurprisingly, it turns out they actually have good acceleration. That is, they get to 0 to 60 very fast. So it's a low time. But they tend to have very poor mileage. Right? And so we can actually start to explore patterns, interactively scrub through the data, and see how different subsets project across 7 dimensions simultaneously. So for example, if I wanted a car that's fast, I could do that here. And then if I wanted to also have good mileage, I can do that here and then see how well do I do. And that's poor mileage. Let's go up here. So many fewer cars, right? But in this way, I can actually explore multiple objectives across dimensions at the same time. Of course, these are all examples of tabular data. So basically, data that you could represent well as a simple spreadsheet or database table. There are, of course, other types of data that we're interested in. So geographic data is one. This is showing all the different airports in the United States sized by their traffic. Of course, they have connections too, though. We have a graph here of the connections between airports. So where are flights serviced to? And so as I mouse around, you notice I can see those connections. But note also that as my mouse gets near a point, it gets automatically selected. So some of these points are really small, so we'd like to make it easy to be able to select them. And so to do that, we actually have a kind of a hidden visualization here where we've actually done what's called a Voronoi Tessellation, which is we just build out the cells such that every point within a cell is nearest to that blue point within it. And that way we actually get this nice acceleration structure that makes it easier to select points. So in this way, trying to make it easier for people to use the mouse to interact with their data. Here's another example of a graph. This one, in the case looking at software engineering. So each node along the periphery here is actually a source file. So this is just a file containing code. And they're grouped into packages. So you have a package hierarchy to a software project. And on top of that, you have dependencies. So certain files will then import other files, and you want to understand the structure of your software project. So in this case, I can mouse over, and I can see the connections, both incoming and outgoing dependencies, to try and understand the graph. And notice some of the tricks we use to try and make this visualization more helpful. If I had drawn the edges as straight lines, you get something like this, which is not particularly enlightening. But by actually routing the edges intelligently using the package structure, so the hierarchy we know of basically the directories in which the files live, we can bundle the edges and actually see larger scale groupings between different sub-projects within this larger project. And then of course we can still mouse over to see individual issues or links for specific files. And then finally, we want to be able to transition between many different representations. So here's a kind of a gallery of animated transitions showing different ways of representing the same data set. I don't recommend all of these, and in fact, I find this reel somewhat gratuitous. But it does give you a sense of all the different representations and also transitions between them you might consider when looking at data. And so again, while you might not want to use all of these representations, you also want a language expressive enough to allow you to explore and invent new techniques. And so I don't think any language is sufficiently powerful unless it allows you to say something silly. So all of those examples were built using data-driven documents, d3.js. And this is basically a library that allows you to take data and then bind it to elements within a web page and parameterize their properties, whether that's visual properties, textual properties, et cetera, based on data. So basically, it's a way of transforming data into documents, hence the name. This is now something you can download. I know a number of you are using it here. It's an open source project where we've been quite surprised and pleased with its success. It's actually currently the 5th most popular project on github.com, which is a popular website for sharing open source projects. And many of you may have used it without realizing it. So for example, all the election graphics done in 2012 by the New York Times, were actually, most of them were done with D3. In this case, this is a decision tree showing different ways either Obama or Romney could win the White House, and including in orange and down here, the different ways they could have actually resulted in an electoral college tie. If you have teenage kids, they might have seen D3 without realizing it too. This is actually visualizations used at the MTV Music Video Awards. This was done by our friends at Stamen Design down in San Francisco. And what you see in all these monitors and also live on the web is real-time visualizations of Twitter traffic as the VMA awards proceed. And so while we set out to build tools for scientists and analysts, et cetera, we also inadvertently provided some infrastructure for Lady Gaga's Twitter tracker. And so this is one of the things that we care about, is building these really expressive visualization tools that people can create interactives and also hopefully push the boundaries of the genre, particularly in journalism and in entertainment. We're seeing new forms of visual representation being increasingly explored. But that's only one part of the problem. In the type of analytic workloads that we're currently seeing industry and academia work with, visualization techniques often have scalability problems, right? So if you try and plot thousands and thousands of points at once, even if your computer does that very quickly, you're left with something that may not be perceptually effective. So you have to figure out, how do we represent data in ways as the number of points go up to make the representation stay effective? And then there's even a much more challenging question of, how do you then make that interactive at large data volumes? So here's one challenge problem we put to ourselves, which was, well, how can we visualize and interact with billion-plus record databases in real time? And we're not the first ones to think about some of these problems. There's actually interesting work in statistics going all the way back to the 80s in terms of how to make visualization scale. But one real common practice in industry today is actually just sample. Well, if I have a nice representative sample, can I just use that and not worry about the billion elements, just use a much smaller set? And in many cases, that works well if you want to find central tendencies or particular trends. But in other cases, it really doesn't fit the bill. So here's a state-of-the-art system, Google Fusion Tables, where they actually built a really nice geographic stratified sampling algorithm to provide an overview of a data set. And the data set here is actually over 4 million check-ins on a mobile social service. So people go to places similar to Foursquare, check in, and then you want to understand user behavior on this service. And using this visualization, we actually only have a very small subsampling of the total number of points. And we see that mostly people live in cities, and then there's a little bit of scattering elsewhere. Larger scale trends, patterns, and outliers can be quite difficult to spot. So we've been exploring different techniques that try and show you more of the entirety of the data at once. So for example, here's a technique of bin aggregation, really just building a heat map. We chop up the world into really small bins and then just count the number of check-ins within each bin to try and get an overview of the full data set. And doing that, we already see a lot more. One, we get a sense of coverage of the service. We get a sense of interesting patterns. Certainly, that it might be hard to see here, but there's like red and orange dots around the major cities. We have these spikes in usage. And then there's other things too. So for example, the number of check-ins along the interstate highway system, the existence of Canadians and Mexicans. What else? We have the an interesting trend coming in here, which is that someone on a cruise ship will actually know that's someone who created a fake account for Hurricane Ike and used the service to track its progress with each day. So it's already starting to give you some insight into both like the adoption of the service and maybe some of the more interesting user behaviors that people have. So this is one where we start thinking about different ways of grouping the data to support more scalable representation. But what about interactivity? So for example, in addition to this map, maybe I want to understand something about time as well. So for example, month, day, and hour. And then I want to understand the connections between those variables. So again, using this technique of brushing and linking, I can explore basically how different groups of people, whether it's check-ins in January or certain times of day, how do those project geographically? Or if I look for particular geographic patterns, do I see any interesting patterns with respect to time? So these are standard interaction techniques, but they come much more difficult when you have really large data sets. So for example, even this relatively small data set where we have just over 4 million check-ins, if we represent it in terms of its possible space, we bin it. Turns out in this particular case we have what we call a 5-dimensional data cube. So we can bin x and y geographically, and then we have 3 more dimensions for hour, month, and day. And in this case, we have a 5-dimensional data cube. And if you took all the possible bins, it turns out it's really large, 2.3 billion bins. Now, it turns out it doesn't matter so much in this case because most of those bins are empty. So we can use what we call a sparse representation. But it turns out as data gets bigger and bigger and bigger, it also gets denser. That what used to be an outlier is now exceedingly common, and you have outliers that are much, much further out. So as these data cubes fill up, you really do have this problem of then running queries automatically. So, running queries quickly across very large data sets. So for example, if I want to be able to see how all the people in January project on the map, I have to identify all the bins for January, compute sums across over all those bins, and then visualize the result. So one question is, how can we do this in a way that allows real-time interactivity in a web browser? And we actually took inspiration from existing mapping systems like Google Maps. And of course, they keep a relatively seamless experience of exploring the world by breaking up the world into tiles and then just serving you those tiles on demand. So that as you pan and zoom the map, you give just the data you need to be able to see the world at that level scale. So we wanted to build on this idea, but of course we need to do this for multiple dimensions, not just 2 dimensions, but many other dimensions of the data set. So this led us to a concept that we call multivariate data tiles. And so the first idea is that rather than send pixel images, like as you see with Google Maps, we really send the data. So that way we can render it dynamically, query it dynamically in the web browser. And the other is we need to send multi-dimensional data. So instead we have flat tiles, we send tiles that are maybe 3 or 4 dimensions of data at once. And so to give you a sense of how this works, we can maybe break up the map into regions. We have 4 regions here, plus we have these 3 bar charts on the side. So one multivariate data tile might just be, give me the data for the upper quadrant of the map plus the month histogram. And then do that for the other histograms. And then I can do that for the other parts of the map as well. So now I actually have 12 data tiles. They're kind of a patchwork that we bring together to get appropriate coverage over the data. And then finally, we have one final tile for just, the 13th tile is the 3 histograms here. And so what did we do here? Let's look at this from another way. We have this full 5-dimensional data cube. We can actually project it out. So basically sum over some of the dimensions to get these projections. In this case for x, y, and hour, x, y, and month, et cetera. And if some of these are big, since like geography might be very large number of bins, we can subdivide those as well. And one interesting question is, well, here we have just 3-dimensional cubes that work for this geographic example that I showed you. Well, how many dimensions do I need for other examples? Well, it turns out you really only need 4. Because if you're just dealing with 1D or 2D plots, the most dimensions you need simultaneously is 4. For example, in a case where you might have 2 maps or 2 scatter plots that are completely disjoint and you want to be able to link between them. So we actually have a really nice bound on the number of dimensions that we need in terms of the data tiles that we send over the wire. And of course, then we can subdivide these tiles further as needed. It turns out we go from about 2.3 billion bins down to still large, but much more manageable 17.6 million bins. And by compressing the data, we're actually able to send that over as binary data that's actually less than a megabyte. And so this is the basic idea is take really large data sets, but pre-compute summaries that allow us to interact with them quickly. Now we still have to query over a couple million bins at once, so we want to make that fast. So I'm going to skip some of the details here, but what we also do is find ways to move the computation down onto the GPU. There's actually 3D graphics technologies such as WebGL that we can now access in web browsers. And by taking our data and embedding them as images, we can actually use the parallel hardware of our graphics cards to do really fast queries. And that allows us to do real-time interaction with these data sets. So for example, in one benchmark, we looked at taking data sets where the original data is basically increasing by an order of magnitude at each step, from 10,000 data points to 1 billion data points, and then measuring in terms of frames per second, how fast does the screen update, can we query and visualize this data. And so as a baseline, we looked at, we wrote our own database that runs in JavaScript and just basically does sequential processing of the data. We get okay performance, about 10 frames per second. But as I talked about earlier, the data starts out sparse, but as it gets denser and denser, you require much, much higher memory to keep all that data, memory resident. And so after 1 million data points, basically we lose that advantage. We can no longer fit the data, and so basically we can't do it in the browser anymore. Whereas if we load the tiles on demand, as I was describing, and then do the query processing in this parallel fashion, we actually sustain over 50 frames per second performance, even when we're looking at summaries of over 1 billion data points. So in this way, by finding the right ways to represent the data and give just what we need to support the level of interactivity that we want, we can actually still create this real-time exploration of even very large data sets. So these are some of the challenges that we try and deal with visualization. Now, to kind of wrap up the talk, I want to talk about just one other project, and that's really at the intersection of visualization and modeling. So even once we've explored the data, we have a good sense of it, it's well structured, and now we want to start doing prediction or using machine learning techniques to understand it in other ways, or maybe at scale. Can visualization still play an important role? And the answer is yes. So we actually looked at this in the case of text analysis. So we were building visualization tools to try and understand the spread of ideas in academia. So we were actually part of a grant from the president's office at Stanford, and he wanted to be able to answer questions like, when I pay $10 million for a new building in an interdisciplinary center, does it impact the research in ways that I can measure? And there's different ways you might want to measure it, looking at collaboration networks, funding, et cetera, all very important techniques. We wanted to answer that question at the level of the text itself. Do you actually see interdisciplinarity reflected in the dissertations that are produced? So we asked the question, can we track the shifting similarities between Stanford departments over time? And this led us to a tool called the Stanford Dissertation Browser. And one of the challenges we had is that we first thought, okay, we'll use standard NLP techniques to compare the similarity of text documents and then iteratively design a visualization for that. And it turns out what happened is that we actually pretty rapidly arrived at some useful visualization designs that revealed lots of problems with their underlying models. So for example, here are 4 different projections using different choices of a similarity function. So we might just look at the words within documents and compare that. There's like common techniques such as TF-IDF and cosine measures, if you're familiar with that. In other cases, we use statistical techniques called topic models. We actually try and understand how do words group together to form meaningful themes, and then compare the different dissertations and therefore their grouping departments based on how those themes shift. The problem is that these algorithms often have lots of parameters and can be difficult to interpret. So for example, one, we said, okay, we have these projections. Well, projections, we've taken all the similarities and mapped them down to 2D. We can get models like here's science and engineering, which is in blue and green grouped together. Health sciences and biology are in purple, and they're over here. And you can see how the med school is close to biology. Then we have things like, we have the social sciences and then out to the humanities. So the overall structure of the university looks pretty good. But what about the individual differences? We really want to be able to look at nuanced changes as we animate these graphs over time. And so to do that, we created interactive views where we can move through different levels of detail. So for example, one thing we do is select a department. In this case, I believe it was English. And then say, we'll group all the departments around it radially based on how similar they are to that center department. Can anyone see what a potential problem is here? So here we've put English in the center, and we see that basically the entire humanities have been clustered together into one single thing, basically saying there is no difference among the majority of the humanities. And so this is a bit of a problem for a number of reasons. So one is it's wrong, right? So we actually do have kind of a priori hypothesis that there are meaningful differences amongst these departments. 2, at the time I was an assistant professor, pre-tenure, and so walking around showing this to people seemed like a really bad idea. 2, and then 3, well, what's going on here? Can we actually understand what the model is thinking? Well, in this case, what we did was the underlying model where we choose the number of topics was actually parameterized using a common technique, what's called we optimize the perplexity on held out data, which is basically just a heuristic for saying how can we pick a good number of topics. And in this case, while that's a standard in machine learning research, it turns out it's a bad choice in that it collapsed all of the humanities into this single topic. So we actually had to increase the number of topics, and then we start to see discrimination amongst these different departments. But that's still really unsatisfying in the fact that we have to have, explore lots of parameters. Can we come up with a better way? So we actually use these visualizations to get feedback from domain experts. So we show people different graphs, and they can label it when they thought a grouping or a similarity seemed right or it seemed really off. So this gives us some sort of subjective baseline to begin to reassess our models. And in the process of doing this, what we realized is that we had one major false assumption underlying every model that we tried. And that false assumption was we assumed that distance should be symmetric. That the distance from department A to department B should be the same as the distance from department B to department A. And so let me give you an example of that. So Stanford has a world-class computer music program called Karma, and it's housed in the music department. So it's not at all strange to say that music is close to computer science. But computer science has very little, if any, music work, and even very little audio processing work as well. So it would be strange to say that computer science is close to music. And so we actually invented a different modeling technique based on a supervised version of topic models. So basically we first said, okay, based on a set of dissertations, what are the common words used within each department? And then we can model how much one department seems to be borrowing the vocabulary of another. And that allows us to create an asymmetric measure, which in this case successfully finds that indeed, if you put computer science in the center, music, while closer than some others, is still rather far away. Whereas if you put music in the center, music actually borrows a lot of the terminology of computer science and signal processing, et cetera, so you see that closeness. And along the way, we actually not only came up with an algorithm that has a better fit with the different judgments we got from domain experts, such as professors and grad students, we also came up with an algorithm that has fewer parameters. So that means there's less uncertainty in terms of the choices of how to use the model effectively towards this data. So this is just one anecdote of how design and taking domain expertise into account can still really lead the way to more effective modeling choices. And so there's much more we could discuss, but we're running short on time. And so hopefully what I've done in this talk is, one, illustrate that looking at the life cycle of analysis in its entirety kind of brings a new perspective and allows us to identify interesting problems that by taking a human-centered approach and understanding how can we build interactive tools for those challenges, kind of opens up both interesting research opportunities, but more importantly paves the way for building tools that will allow us to more effectively work with data. So with that, I'd like to thank you for your attention. If you're interested in any more of our software projects, of our papers, et cetera, you can learn more about our group and our work here at the Interactive Data Lab, idl.cs.washington.edu. And I'd be happy to take any questions you might have. Thanks. Yes?
What about resolution? Is that scalable? Can you take it off the web and make high resolution pictures?
Oh, resolution. Yeah, so it really depends on the tool. So in this case, the stuff we're doing in particular with D3, it's like binding to elements of a web page. So the typical way you build out a visualization that way is actually by generating elements using SVG, which is scalable vector graphics. So rather than just pixel level resolution, you're really actually describing the underlying geometry, which means then you can render that out to a PDF and then you get almost like an infinite zoom, right? Things like that. And if you're interested in static graphics. And in fact, that's how we make almost all the charts that we produce in our research papers now too. Yeah.
More questions?
Yes?
This is a very simple question, but when it comes to using D3, from a user perspective, do you enter the data, give it some idea of what you want, and it produces things for you, and you say, not quite, and you tweak it? Or does it require coding on the user side?
So D3 is a coding level framework. So it's basically a library written, in JavaScript, so it runs in the browser. So it's basically, it's what we call a domain-specific language. It's basically like a language embedded within JavaScript, kind of has its own conventions, but basically you load in data and then you specify through a series of rules how you want properties of that data to be mapped to different types of shapes and parameterizing the properties of those shapes. And so it's really intended as a low-level tool for really allowing a very expressive wide space of design. Now that said, there are a number of other projects and tools that are higher level that kind of maybe try and help automate part of that process of visualization design. And so we're about to release in a couple weeks actually a tool called Lyra, which is basically a way for trying to do D3 type design without programming. So So it's more like Illustrator meets Excel and D3 in a new environment. So that's certainly reducing the programming burden is something that we care about deeply in our group. Others have looked at techniques for doing automated visualization design, and we haven't released tools along those lines yet, but we do have active research projects there. And other tools, so you might be familiar with Tableau, a local company that's been fairly successful in recent years. So they provide a way to build up visualizations very quickly, and also you have some suggestion capabilities for different visualizations as well. So hopefully that answers your question. Yeah?
How do you think people should get started if they want to start building interactive data visualizations from their own?
So there's a couple ways to get started. I think first is you want to start having a good understanding of what basic understanding of principles that underline good visualization design. And there's a number of books and tutorials online. I actually like the books by Stephen Few. Tufte, you may have heard of, has great books, but they're very inspirational. Where some of these others, including Stephen Few's books and Alberto Cairo's books, give you a more straight shot, heads-on, like here are things to think about in the design of graphics. And then there's various ways to get started without even having to dive straight into JavaScript code and building out things in D3, which is still a perfectly fine way to get started. There are a whole variety of tools. Like, for example, if you're used to programming in R or in Python, there are great graphics libraries that you can start to build up using kind of simpler syntax and then start to customize them yourself. You might look at other sort of consumer level tools like Tableau, and also actually lets you explore a space of visualizations very rapidly. And I actually use tools like that to prototype. So I actually explore a space as quickly as I can using consumer level visualization tools, figure out what I can't express, but then it kind of informs, and guides my actions when I then go to write code. So I'm not just doing all of that exploration in code, which can be sort of a time sink. Yeah?
So what's the name of your visualization language?
So the one we were just talking about is D3, data-driven documents. But then the interactive tool that we're talking about on top of that is called Lyra. And so that's going to be released in a couple weeks.
You could program and it's domain specific to visualization. Oh, no, data transformation.
Oh, the data transformation language? So that was Data Wrangler. And the first thing I showed. And the underlying language is, strangely enough, called Wrangle. So. Cool. Yeah, Mike.
How do you think the use of these types of visual tools can help balance the use of expert opinion versus the use of strict statistical tests? How does that play a role and manage across what can sometimes be attention?
Yeah, it's an interesting question. So basically how you play this different tension between, I guess, statistical expertise and perhaps domain expertise. And this can arise at different levels, right? So as I demonstrated in the talk early on, someone with domain expertise may be able to spot, things in the raw data and say, like, they just can't be right. Like, there's an error in data collection, or we're missing something really important, or this whole segment of people who are really important aren't being included in this data set, right? So all throughout that exploration process, it's important. And in fact, visualization is really helpful for model verification as well. So you can visualize the goodness of fit of a model, like looking at the residuals, for example, and there's all sorts of techniques there. And so that's where I find that in most companies I talk to, the people who are trained as data scientists have to develop some expertise about their business to have that. And similarly, they have teams where like people from a particular business will work with a statistician or domain expert. So it's really about having both components there side by side. And then there's a whole other issue, which is around communication. And that's where, how do you build the graphics that tell the story effectively, accurately, allow people who might be, 1 or 2 or sometimes 3 steps removed from the actual data analysis to make an effective decision. And so that's a real important topic, but one I probably can't do justice to in like a 20-second response.
Well, if there are no more questions, let us thank our speaker again.
Thank you.